the matrices and linear systems and some preliminary notations and definitions. Real space Rn. So what is the definition? Here R denotes a set of all real numbers. Rn defines n tuples that are ordered list of real numbers. So in that sense, Rn you can define as n numbers that are ordered. Each of those numbers belong to the set of real numbers. So we call Rn a vector, and also it could be a column vector, or it could be a row vector sometimes. The next concept is defining addition and scalar multiplication. Addition, if we are adding two vectors with the same dimension, each of them having a dimension of n, then for addition, you add each of those elements together and continue all the way until you add all n elements together. If you by scalar and also addition of vectors. So a vector space, what is the definition? The vector space is a space that you have two different operation, addition of vectors and a scalar multiplication. For addition, you can have two vectors from the space V. If you add them, the result would be another vector that belong to the same space. If any two vector you choose from the vector space V, then the addition of those two belong to the set of V2. A scalar multiplication is the same. If you choose any vector from the vector space V, you multiply it by a scalar or real number, the results would be another vector that belongs to the set V. So a vector space will satisfy some specific standard axioms such as closure, associativity, commutativity of vectors, addition, commutativity of vector addition, existence of a zero vector, existence of additive inverses, compatibility, and distributivity for scalar multiplication. So what do they mean? If we choose any three members from the set V called U, V, and W, and also two scalars, A and B, from real numbers, then all these properties hold. The first one is the closure. If you add the two vectors, the result will be another vector that belongs to the set V or vector space V. Also, if you add the three vectors, you have the associativity in a way that if you add the first two vectors and then add with the third vector, the result would be the addition of the second two vectors, V plus W, plus the first vector. Also, we have commutativity of the vector, where V plus U plus V would be equal to V plus U. Also, we have existence of a zero vector, where any vector you choose U from the set V, there exists a member in the set called zero vector, where if you add that to any U vector chosen from the V, the results will be again U. That means there exists an additive invert for this case, any U choose from the V space. There exists a negative U that if you add to the U, the result will be the zero vector. Distributivity, compatibility, and distributivity for scalar multiplication, where if you choose A and U, where U is a vector, A is a scalar, if you multiply them together, the results will be another vector in the set, in the vector space. Also, if you have A and B, if you multiply B by U and then multiply that by A, the result would be the multiplication of the first A and B, which are scalars, and then multiplication of that result in U. Also, if you have a scalar times U plus V, the results would be A times U plus A times V, which is distributivity for scalar multiplication. Also, if you add two numbers or scalars and multiply them by a vector, the result would be the multiplication of the first scalar by the vector plus multiplication of the second scalar by the vector. And if you multiply any vector u in this set V by 1, the result would be u again. So all these properties hold for a vector space. So when we talk about the vector space, all these properties, they hold with regard to the operation of addition and scalar multiplication. What are the examples of vector spaces with all these properties? So some are, for instance, polynomials. Another one is the space m by n real matrices.